So yeah, hello everybody. My name is Tanguy Coquio. So I'm from France Energy Marine, and in the FLOWTOM project, I was involved in the numerical task, but also in the basin test campaign. So in this part, I will show you the comparison between the basin test results and the dedicated numerical model built for the occasion. So, as said Benoit, we are looking here at two bodies, a single hull vessel and the semi-submersible Volturn USS, mounted with the IEA 15 megawatt turbines. All of it is at a scale of 150. What we want to do here is to reproduce what is happening in the basin in the numerical model, to be able, in a second step, to have confidence in a numerical model to process the full study of the FLOWTOM project. So here we just want to match to the basin. This is why we have taught mooring lines, for example, just as in the basin, and it will change. It will change after. So the numerical model was built for this comparison in CIMO, operated in the CIMA workbench. We are representing the hydrodynamic effect with the radiation diffraction models. The stiffness used in the model is linear, and we take into account the drag forces and drag effect on the hulls by the mean of quadratic and linear additional damping. So mostly roll additional damping for the hull, and a lot of damping for various degree of freedom for the semi-submersible with more recent elements. The analysis was computed through frequential and time domain analysis, depending on what we wanted to look at. And as I said, the mooring is represented taught mooring lines, but was calibrated through a catenary chain equivalent mooring stiffness in the complete study. For the dynamic positioning, we are looking at linearized stiffness matrix with additional linear damping to represent the DP that we have seen with the spring in the presentation of Benoit. What is the objective of this basin test campaign and of this comparison? It is to have a good confidence in the numerical model that we are using to produce the main result of the of the FLOWTOM study. To do that, we want to look into detail at several effects that we want to be confident with, especially the coupling effect between the bodies. So we introduce coupling in the numerical models. So we want to see if these coupling effects are accurately captured by the numerical model, and if so, is it in the good range of period. We want also to be confident in the stiffness and damping representing the behavior of each body. So we can have a look at that by the comparison of decay test and RAO comparison, as I will show you later. The calibration of the main FLOWTOM numerical model is the finality of all this work, to be able to well represent the behavior of the Volturnus model as a single body, of the vessel as a single body, but also as the two bodies coupled in the same place. Understanding the low frequency motion is also an objective of the FLOWTOM project, but will not be presented today in this webinar. You can see here a representation of the schedule of the 2 weeks basin test campaign. So as you can see, we have looked at different type of experimentation. We applied on the floaters regular waves, irregular waves produced from a joint swap spectrum. We also produced some decay tests, and you can see in yellow there is a lot of phases of to change configuration. As mentioned, Benoit, we needed to change the mooring point, for example, underwater, which was kind of tricky because we needed the divers to do so. We looked at 4 configurations between the floater and the vessel. Configuration that are named 0, 19, -90, and 45 degrees. As you can see, depending on the orientation, the vessel can be can be applied as a shelter or as a reflecting the waves compared to the floater. Applying regular and irregular waves, we went from 1.5 meters each wave to 8 meters regular waves, going through 7 seconds to 21 second period. For the irregular waves, we went from 1.5 meters HS to 11 meter HS, and going through 7 to 6 to 20 second period range. So of course here we do not intend to validate operational operation with this kind of 8, for example 8 meters or 11 meters, but it's more for the interest of calibrating the models. So in this first part, I will describe you the results coming from the decay test produced in the basin. So in the basin we looked at 4 kind of configuration. The vessel with dynamic positioning, so it's the spring that Benoit presented you before. The vessel free floating, so meaning there is nothing to maintain the station keeping of the vessel. The Volturn USS with mooring, and the Volturn USS free floating, so with no mooring. And with this kind of configuration, we compare them with 3 types of numerical models. The models that are so-called raw and the models that are so-called recalibrated. The models that are called raws are just the models that are built in the first place with the specification, so just with what Benoit presented, and recalibrated are the model when we take into account necessary recalibration of different parameters, as I will show you just after. The vessel was needed a recalibration, so this is why there is only three lines here, where the semi-submersible floater was not using this recalibration. So we will only look at the raw model. And so the decay test objective is first of all to understand the impact of mooring and DP on the global behavior, and to recalibrate the stiffness and damping data if necessary. So in this slide, we are only looking at basin test results, so there is no numerical output here, and we are comparing for the vessel under the vessel free floating versus the vessel with dynamic positioning, so meaning with spring, and just to look at the impact that this spring can have on the vessel. What we have to understand here is that the station keeping system of the dynamic positioning is meant to control the surge motion, the sway motion, and the yaw motion, but should not impact the heave, roll, and pitch motion. So this is what we are looking at here: the heave, roll, and pitch motion that should not be impacted by the station keeping. Point of attention is that the decay tests were performed using a long stick in the basin, and this is why the initial state of the decay are not the same for each test, because it was difficult to reproduce the exact same test with the decay. So this is what is displayed in red here: difference in initial decay position. So this is something to keep in mind when you look at two curves that are put together. What we can see here is that there is a low impact of the dynamic positioning system in the basin for the heave and the roll, but an important impact for the pitch motion. Though in the heave and roll motion there is a stiffer response, so meaning a lower natural period for the basin with the dynamic positioning compared to the free floating, which is due to the addition of stiffness with the spring, so that makes sense, even if we wanted to avoid that. And for the pitch, we have a lot of damping with the addition of the dynamic positioning. Just if we can just come back to the last slide. Yeah, so this is something to look. Yeah, it's okay. Thank you, Laura. In fact, I have said everything. My bad. In this slide, we will look at the basin vs numerical now. So now, when I compare the basin vs numerical, it's always the numerical, the basin where there is the dynamic positioning or the station keeping with the mooring. So this is the case here. So in regular line, you have the basin result, and in dashed line, you have the numerical result. It can be raw when the numerical model is untouched and dedicated to the basin, or tuned when it's touched to it's tuned to represent the best way possible what's happening in the basin. So what we can see here is that we have difficulty in search sway to have the correct damping on the numerical model. This is something that was recalibrated. We also touch a little bit the stiffness to go to the second semi-tuned model, which is accurately representing what is happening in the basin. Though we are very happy with the first result, because there is a lot of additional station keeping elements on the mock-ups, and this is considered as a light adjustment on the numerical model, and especially it's dedicated to the representation of the model in the basin, not of the global numerical model. So yeah, we tuned a little bit the hydrostatic stiffness, and we add linear and additional quadratic damping here. Same comparison, but for 3 other degrees of freedom: the roll, the pitch, and the yaw. Here we can see that in roll we are very close to the definitive results with the raw model. A little adjustment was done for the stiffness to match the natural period of the basin, but still it's a nice result here, and the damping is well capturing the eddy making of the hull plus the bilge keel that we implemented in the model. So we were very happy with that as well. For the pitch and yaw, we had some slight adjustment to do to reach a perfect match between the curves, and it's not a perfect match, as you can see for when you go for the last oscillation of pitch and yaw. It's difficult to match what's happening in the basin, because motion are superimposed between different degrees of freedom, and then it's difficult to have a match between the numerical model and the basin. You can go to next slide. Here is the same comparison, so basin vs basin, but for the volturness. Here we are looking at 2 degrees of freedom, the heave and the roll. We can see that in the same spirit as for the vessel, the addition of mooring lines is impacting the motion and is creating damping and stiffer response than for free floating. In this case, this is something that was expected, because the heave and roll motion are some degrees of freedom that are impacted by the presence of mooring lines, when it was not the case for the dynamic positioning. And so it's just to quantify this impact, but it was expected. And so there is also the introduction of damping by the presence of the mooring lines. If we now go to the comparison between the model and the basin, the numerical models, here there is only the raw numerical models, because we decided that the results were satisfying to be used for the RAO analysis that I will present you just after this section. In fact, the calibration of the Morrison element on the semi-submersible is something that is known in the literature, and as we obtain this kind of results for heave, roll, and yaw, we thought that it was better to stay consistent with the Morrison, the drag Morrison elements that we put on the model, extracted from the literature, to better than recalibrated all the Morrison elements. We can see that we have a small shift in stiffness for the heave on the left here, but still the first oscillation are very good, and so we decided to stay like this. So no tune parameter for this model when I will present the RO comparisons. So to conclude with this decay test, the DP system in the basin is leading to a slight different behavior than the one expected. As I mentioned, we are impacted the roll, pitch, and heave motion with the additional spring in the basin, but still it's a pretty good result that we are obtaining in the comparison between the numerical model and the basin, and we are the implemented system is what we wanted to do in this campaign. After this section, I will present you the RAO comparison. So we decided to tune the model of the basin, so with additional stiffness and damping for the following RAO study. But this tuning is really dedicated to the basin model, meaning there is to take into account the spring and the various elements in the basin, for example, the spring, but is not necessary for the main FLOWTOM analysis, as we are not considering the spring in the main FLOWTOM analysis, but an equivalent dynamic positioning matrix stiffness with additional damping. So it's just for the RO comparisons. So no recommendation for the main FLOWTOM Winsor-Knudsen model from decay test analysis. If we looked at the Voltern USS, the match is good between the numerical and the experience in the basin, and so we conclude that the numerical model is accurate for the semi-submersible motion. So we do not modify it for the next RAO study, and neither do we for the main study of the FLOWTOM project. I will now move on to the wave test. So in this basin wave test, we looked at several configurations. The first one is the vessel single. The second one is the semi-submersible single. We also looked at the both body together. When we can see, as we will see, there will be a coupling effect between these two bodies. And we looked at different orientations: 0 degrees, 45 degrees, 90 degrees, and minus 90 degrees. I will omit the 45 degrees comparison in this webinar. For the numerical model configuration, we will look at the same as the basin test, but with tuned parameters, as I said, for the vessel. For the wave types, we are looking at unidirectional waves, so no spreading in the direction, and we are both looking at regular and irregular set of waves. This wave test objective are to first compare the RAO between the basin and the numerical model, validate the coupling effect between the bodies, validate the damping effect on the floater, and looked at the low frequency motion characterization. So in this presentation, I will only look at the point 1 and 2 and omit the points 3 and 4. Just a small talk about one issue we crossed during this basin test campaign. We realized in the beginning of the first week that we had an issue with the linearity of the spring in the basin for the targeted tension in the line, which is around 10 Newton and correspond to the red dot on the graph on the left. We realized that the linearity of the spring was so this is what it was. There were no linearity, and when we pretension more the system for the yellow point, for example, we were more on the linear part of the curve for the spring. This impact a little bit the result, especially for high period, so low frequency motion of the high periods between 15 seconds and more, from 15 seconds and more. And so we realized that the curves for the natural period of the floater, for example, when it's around 20 seconds, were not realistic for the RAOs with the low pretension. But when we add additional pretension to the system, we were fitting more and more to the to the original curve. So we can see that on the right here, on the red dashed line, you have the numerical models, and with the yellow curves, you have the basin test with a high pretension, and with the green curves, we have the basin test with low pretension. And we can see that we are totally missing the effect at 20 seconds with the low pretension due to the non-linearity of the springs. So we have to be very careful with the result presented after this section, because this part is very tricky due to the stiffness of the spring. Fortunately, we are interested in two main effects, which are the coupling effect and the low frequency motions. And these two effects are happening for low period range, so before 15 seconds or even 20 seconds. And we can see that in this range, this non-linearity issue is not impacting at all the results. So that's good for us. But for the damping effect on the Voltern USS in particular, it's difficult to conclude at range around 20 seconds. So just to keep in mind for the next part. For the post-treatment methodology, so we looked at basin regular waves and irregular waves, as I said before. For the regular waves, it's discrete points that are extracted for the amplitude and phase for the RAO. For the irregular waves, we used cross-spectrum analysis to extract continuous RAO during the to extract continuous RAO. And we concatenate all these results, as we can see on the right, to obtain the best fit. So in the first part, we have a lot of tests that are producing a lot of curves that can be superimposed on the graph, and we use the best average curves around these curves to obtain a single result, as we can see on the right here, a single curve for the irregular RAO. Here there is no regular RAO represented. And for the CIMA numerical RAOs production, this is discrete points extracted from a time domain simulation with a regular waves analysis. So important to have that in mind also. It's not produced with irregular wave time series. I will show you now a couple of results for RAO comparison. So if there is no regular line, it's because the irregular tests were not produced during the tweak campaigns. And so if you have only a cross and dashed line, is the numerical model vs regular waves, as we can see here. In this first result, we can see the single vessel with side waves, so at 90 degrees. There is only regular basin waves here. We can see with the green arrows that there is only a certain direction that are, or certain degrees of freedom that are of interest, because we have the wave from the side. So looking at the surge or the pitch here is not of interest, and we are capturing mostly noise during the test campaign. So please focus on the green arrows. We can see that the sway motion and the roll motion are well captured by the model. For the heave motion here, we have a shift in the peak of response at 7 and 8 seconds. This is not happening again with the irregular motion. So this was not, we did not understand this kind of point, maybe an error measure. And the phase comparison is satisfying for this first result. I can go to next slide. Here it's the same kind of comparison, but with the single vessel with head waves in this case. The same, we have only regular basin wave here. The surge motion and the heave motion are well captured. Slight offset in pitch motion is captured at 6 to 8 seconds, and the roll motion is slightly overexcited in the basin. But this is a parasite motion because there is no waves in this direction. As well, the phase comparison is satisfying here. If we look now at the single semi-submersible floater with side waves, here we have both regular and irregular waves. So as I mentioned before, we have to be careful with the 15 plus period range. Here, the curve that we are concatenated, for the irregular waves are both with low pretension and high pretension for the right part of the graph. So it's a hybrid representations, and we can see that we have a very good match for this comparison between the numerical models and the basin tests, which is confirming the hypothesis of not recalibrating the model from the decay test. I will now zoom into a specific effect that we wanted to investigate during this basin test campaign. It's the coupling effect between the semi-submersible floater and the vessel. What is represented here is only numerical simulations with three types of configuration. The first one is the single semi-submersible floater alone. The second one is both floaters, so the floaters plus the vessel with sideways, but the vessel is sheltering the floaters. And the third one is the same thing, but the vessel is down waves, and so it's reflecting the waves on the floater and not sheltering them. If you go next slide, I think there is a zoom in lore, so we can see. We'll just look at the period of interest that is between 4 and 13 seconds here. Because we just see before that there is no coupling for the range of period above 13 seconds, and we can see that there is three types of motion capture for the semi-submersible here. The first one is the single vessel. It will be the middle curve. So I'm sorry for the color. It's not. I should have chosen another color for the curve. So we'll say the light red is the single bodies. The dark red is the bodies which is excitated because the vessel is reflecting the waves, and the green one is the semi-submersible sheltered by the vessel. So we can see that we have three specific states here with the numerical study, and we wanted to see if we can capture that with the basin test to confirm the model. So this is what we are looking here. So here it's a slightly different representation as the slide before. You can see on the right, it's not the phases anymore. It's only a zoom of what's happening on the left. So here we are superimposing the curves of the numerical model and the basin test results, and we can see that we have a very good match, and we captured with a great accuracy the coupling effect between the body in the basin, which is very encouraging for the use of our main model for the next study in the FLOWTOM project. So we can see that there is an effect of the vessel on the floater when the waves are coming from the vessel or reflecting by the vessel, and this is well captured. On the contrary, if we looked at the vessel and not at the semi-submersible, we can see that this is only numerical, but we capture exactly the same with the basin test, but I will not talk about this today. But we can see that there is no impact of the semi-submersible floater on the vessel. This is due to the fact that this is composed of slender elements on the semi-submersibles compared to the massive vessel and that have not the same mass as well. So there is a minor coupling impact on the vessel. To conclude on this wave result analysis, the tuned numerical model provided an accurate pre-representation of the of the vessel, both for coupled and uncoupled situations. It is not impacted by the presence of the floater in the basin, so there is no recommendation coming from this study for the main floater analysis. For the semi-submersible floater, due to the non-linearity of the basin mooring line, as I presented in the slide before, the representation of RAO for high periods, so meaning period above 15 seconds, are impacted. So this is something to be considered in this study, that we cannot be safe with what is represented above 15 seconds. We are lucky for this kind of study because there is a lot of documentation in the literature for the FOWT-O&M USS, and we can easily fit the curves of the RAO of the numerical model with the existing model. So no impact for our study here. For the lower period, the two numerical models provide an accurate representation of the floater, and we capture with great accuracy the coupling effect between the bodies. So we are very happy with this comparison, and so we decided to not further recalibrate the model for the main FLOWTOM study. To conclude on this basin test analysis, it was a successful basin test campaign. We spent 2 weeks in the basin. Around 150 tests were performed. The mock-up were achieving the required specification, be it for the geometry, mass, and inertia. The innovative system that was proposed by Eframer to represent the dynamic positioning of the body was very efficient and was not polluted much the other degree of freedom, so we were very happy with that. The decay test and regular wave analysis permit to show that there is the radiation diffraction model used in the FLOWTOM project is accurate and well chosen for our study, both for the vessel and for the FOWT-O&M USS floater, single or coupled. So we captured well the coupling between the bodies. The viscous effects are also well captured by the numerical models. We need to be careful when we compare viscous effect in the basin and in the model, as it's not the same scaling, but though it's very good very good match here. So the more recent element on the floater and the additional roll damping to represent the bilge keel drag effect on the vessel are providing an accurate comparison. Natural period of the system are also well captured during these comparisons. For the minor issue that were detected, we have this issue of stiffness linearity for the mooring lines, which is impacted the high periods, and also the dynamic positioning does it slightly impacting the unwanted degrees of freedom of the vessel. But still, we can conclude that we can use the main numerical model of the FLOWTOM study without risks for this kind of comparisons.